Okay, so now this time we'll talk about the Chinese remainder theorem again, but a somewhat more constructive approach which allows us to systematically find a solution. Okay, so I've now titled it the Chinese remainder theorem and the 0-1 idea. So we'll see in a minute that the 0-1 idea that we have looked at in various different contexts also has a nice application in this particular problem. So here's the same question as last time. We said except I'm going to do it a little more generally. So let x be any number between 0 and 7 and y be any number between 0 and 20. The question is find a number n between 1 and 168 such that n satisfies those two congruences. N is congruent to x mod 8 and congruent to y mod 21. Okay, so now let's bring in our 0-1 idea again. So this is the general problem we are trying to solve, but suppose we could do the following. Okay, so let's try instead to solve two problems. So suppose we could solve, well, problem 1, which is I can find a n which is congruent to 1 mod 8 and 0 mod 21. Okay, and so let me say, suppose I knew how to solve this, and let me call that solution as n1. So call this solution as n1. Okay, so similarly, let's say we can solve a second problem as well, which is the congruence n congruent to 0 mod 8 and 1 mod 21 now. Okay, and let's call, again as I'm saying, let me assume I can solve this, so let me call this solution as n2. Okay, so suppose we could do these two problems, then the general problem is very easy to solve. Okay, so let's see why. Then consider, how do you solve the general problem? Consider the following choice of n: x times n1 plus y times n2. Okay, it's define n to be this, and observe that what do you get when you look at the remainder of n? What is n congruent to modulo 8? That's really the question. So observe n1 and n2. So what are they congruent to mod 8? n1 is congruent to 1 mod 8 by construction. n2 is congruent to 0 mod 8. So n will turn out to be congruent to x times 1 plus y times 0 mod 8. Okay. Here I've used the fact that n1 is congruent to 1 and n2 is congruent to 0. So why is this? This is by the properties of congruences that we talked about. So recall, congruences have these nice properties with respect to addition and multiplication. So how do I prove this, for instance? So let me just sketch a proof of this. n1 is known to be congruent to 1 mod 8. So what I'll do, and x is congruent to x mod 8. So this is a trivial statement. I'm not saying anything here. This just says that x and x leave the same remainder when divided by 8. It's more or less a tautology. So here are two congruences mod 8, and last time we had this property which said that when you have things like this, you can multiply. X n1 will therefore be congruent to x times 1. So x n1 will be congruent to x times 1 mod 8. This is the property of multiplication of congruences. So that's how I concluded that the first term x n1 is congruent to x mod 8. Similarly, the same logic applied to n2 will show you that y n2 is congruent to y times 0 mod 8. Okay. Now, so what is this? This is just x, right? X into 1 plus y into 0 is just x. So therefore n is indeed congruent to x mod 8. And by the same logic, if you look at congruences modulo 21, now you'll get n1 is congruent to 0 and n2 is congruent to 1, So that's again y. This is indeed. So n turns out to be congruent to y mod 21. Okay. So the key point is of this is that to solve the general problem, it is actually enough if you can solve two simple problems. One for where you have a 1 0 for 8 and 21, and the other where you have a 0 1 for 8 and 21. This is the classic 0 1 idea that we have been using in many contexts before. And in this case, let me just say, if you could solve these two, so let's actually do it in this example. So the value of n1, so let me just tell you the value of n1. So this can be found by brute force. The value of n1 is 105. So if you look back at that table that we wrote out in the very beginning last time, where we tried to do this by brute force, you will find that n1 equals 105 has the property that it's congruent to 1 mod 8 but 0 mod 21. Similarly, n2, which is congruent to 0 mod 21, sorry, this is congruent to 0, okay, n2 should be congruent to 0 mod 8 but 1 mod 21, so that's 64. Okay. So n1 and n2 in this case turn out to be 105 and 64. And how do I obtain this for now? Well, if you think of it, it's just by trial and error, just brute force. But having gotten this, let's try and solve the problem from last time. Okay. So now suppose I want to say I want to find n which is congruent to 3 mod 8 and 10 mod 21, which is what we tried to do. So in other words, x is 3 and y is 10. So what's the solution give us here? It says, well, since you know the solutions n1 and n2, the general answer is just given by xn1 plus yn2, which in this case is, let's see, x is 3 into 105 plus 10 into 64. Which turns out to be 955. Okay. So doing it this way produces the answer 955, and this may worry you for a minute because remember the earlier answer we got was 115 when we did by brute force, but observe what we are getting by this method is just one solution. Okay. So we are not necessarily getting the smallest natural number which solves this problem. All you are getting is some natural number, or it could even be an integer if if we take negatives here. All you're getting is some integer which satisfies the system of simultaneous congruences. But that's not too bad because we know how to get all solutions starting from any one solution. All you do is just add or subtract multiples of 168. Okay. So if instead of any one solution you wanted maybe the smallest natural number which satisfies this guy, these two congruences, all you do is you just take 955, subtract out appropriate multiples of 168 and see what you get. So in other words, you find the remainder that you get when you divide 955 by 168. Okay, and you'll find that when you divide 955 by 168, so 840 is 168 times 5, and so this is exactly 115 more than that. So 955 is in fact the same thing as 115 modulo 168. Okay. So here's the smallest natural number solution, just 115. So here's a second approach which allows us to solve the same problem, but still this requires one brute force step, right? How do you find n1 and n2? You now have two problems to solve, and if you are finally going to solve both of them by trial and error, this seems like it's actually more work than just trying to do brute force directly on the original set of congruences. Okay. So this approach is useful only if you can have a more systematic way of solving for n1 and n2, okay, without using a trial and error thing. So that's the approach I will describe next. So what we want is the following thing. We need a systematic or more algorithmic approach, to find n1 and n2. Okay. So in order to do this, so let me just talk briefly about something called the Euclidean algorithm, which may be familiar to you. So what does a Euclidean algorithm do? So let's just do it by example. So given two numbers, it finds their greatest common divisor. Okay, so that's the point of the Euclidean algorithm. So given two natural numbers, if you wish a and b, it's an algorithm which finds the greatest common divisor, the GCD of a and b. Okay, so what does the greatest common divisor mean? It just means, well, you do the following: you take all natural numbers n which divide a and which divide b. Okay, so such a thing would be called a common divisor. Numbers which are factors of both a and b, and amongst the numbers in this set you find the maximum. So it's a maximum number in this set of n such that n divides a and n divides b. That maximum element is what's called the greatest common divisor of these two numbers a and b. Okay. So now the Euclidean algorithm, so let's apply it to the two numbers 8 and 21 that we started out with. So recall 8 and 21 have no common factors, so we already said that before. In other words, there are no common divisors. So 8 and 21, if you look at what the common divisors are, well, you'll only get 1. The number 1 of course divides everything. So 1 will divide 8, 1 divides 21, but other than that there aren't any other numbers n. Okay. So the GCD of 8 and 21 is 1. So sometimes we express this by saying they are relatively prime. So now what does the Euclidean algorithm do? Okay. Given the numbers 21 and 8, and suppose you did not know to start with that they were relatively prime. Okay. You want to find their GCD. In general, given two numbers, how do you find their GCD? So here's what the algorithm says: you perform a set of successive divisions. So look at 21 and you divide 21 by 8 and find the remainder. Okay, so 21, I divide 21 by 8. Let's see, what do I get? 8 2s are 16 and I get a remainder of 5. Okay, so in other words, this is the thing that we have been doing. We have been writing 21, you write it as some, so let me just do this. 21 can be written as 2 times 8. So I divide 21 by 8 and I get a remainder of 5. Okay, so here's the remainder 5. So now what do you do beyond this? Well, so what does the algorithm say? It says the following: now instead of 21 and 8 as being the two players in the picture, you now replace 21 by 8. Okay, and think of 8 and 5 as being the two players in the picture. Okay, so maybe I'll just box this as well, because that's going to be something that enters the algorithm now. So I write 21 as some quotient times 8 plus a remainder, and instead of thinking of 21 and 8 as being the two important entities, I replace them by 8 and 5. Here what does that mean? I divide 8 by 5. So next step of the algorithm is the following: you try to divide 8 by 5 and again find the quotient and remainder. So 8 divided by 5, quotient is 1, remainder is 3. Okay. Now the same thing. So whatever the two numbers on the right hand side, 8 and 5, you divide the larger by the smaller. Similarly, I have 5 and 3, I divide 5 by 3. Okay. So I write 5 as, I divide 5 by 3, find quotient to be 1, remainder to be 2. Do it again to 3 and 2. So I finally get 3 is 1 times 2 plus 1. Okay. And if I do it once more, if I write 2 and 1, if I write 2 as some multiple of 1, so I could do this once more, I write 2 as some quotient times 1 plus a remainder, but now the remainder is going to be a 0. Okay, so you keep doing this algorithm. So this is the Euclidean algorithm. You keep performing successive divisions to find successive remainders. Now finally when the remainder becomes a 0, so at some point it will become a 0. So what you do at that step is, well, you forget about that step. You just look at what you got one step preceding to that. Okay, so I forget the last step. The preceding step, there would have been a remainder. That remainder is the GCD. That's what Euclid's algorithm says. So in this case, the final non-zero remainder, this fellow here, is in fact the GCD of the two numbers. of 8 and 21 in this case, or more generally if you had any a and b and you kept doing this algorithm again and again, the final non-zero remainder that you obtain is the GCD of the two numbers. Okay? So that's the Euclidean algorithm. But what's the GCD got to do with trying to solve for these two congruences? How do we find n1 and n2 from these congruences? Look at something more that you get from the Euclidean algorithm. So you should think of the Euclidean algorithm as being a set of 4 such equations for this particular example. Okay, there are 4 equations. Now the final equation, which says that the GCD is a 1, so let me sort of read these 4 equations but from bottom to top. Okay, so I turn the sequence around. I start from the end. Okay, so I will write 1, that was the last remainder, as well, what is it? It's 3 minus 1 times 2. Okay, so I'm going to write the remainder alone on the right. So I've now written 1 in terms of 3 and 2. Okay, so again now I mean recall I'm trying to do this in reverse. So 2 I will now replace with, so instead of having 3 and 2 I will try and write things in terms of 5 and 3. Okay, those were the 2 players in the one preceding step. And in going further, I will replace 5 and 3 by 8 and 5. Okay, so I want to keep replacing the 2 active numbers by what was active one step preceding to that. So what will I do? I will write this as 3 minus 1 times. So I will read my equation, the one preceding equation said that 2, okay, so maybe I should just, maybe I will do it on this board. Okay, where it's easier to also see the original sets of equations. So I start from the last equation. I write this as 1 equals 3 minus 1 times 2. And so going one step further, the 2 I will write as 5 minus 1 times 3. Okay, so this would be written going equal to here. The 3 I will leave as it is, minus this 2 I will write as 5 minus 1 times 3, okay, or 5 minus 3. So this expression, let me simplify a little bit. What's this? This is 3 plus 3, so it's 2 times 3 minus 5. Okay, so now I have written the 1, the final GCD, in terms of 3 and 5. Okay, so now again I will go further. I will replace the 3 in terms of whatever I get one step before to it. So the 3, for instance, here is 8 minus 5. So I will replace the 3 like that. I will write it as 2 times 8 minus 5 minus 5. So let's simplify. It's 2 into 8 minus 2 into 3 into 5. So it's 2 times 8 minus 3 times 5. Okay. So last step, I will replace the 8 and the 5 by the 8 and the 21. In other words, I will write the 5 as 21 minus 2 times 8. So let's do that. It's 2 times 8 minus 3 times 5 becomes 21 minus 2 times 8. Okay, so this is just the Euclidean algorithm in reverse, where the idea finally is to write the GCD back in terms of the original 2 numbers. So what is this? So let's simplify this a little bit. This is 2 into 8 plus 6 into 8. So this is 8 times 8 minus 3 times 21. So finally what do I get? I get the following equation when I finish this Euclidean algorithm in reverse. It just says that the GCD 1 is actually the following combination. It's 8 times 8 minus 3 times 21. Okay, observe I've done this completely systematically. I didn't need to know what these numbers A and B were. This procedure can be programmed on a computer, for instance. So all it's saying is just keep going backwards one step at a time, substituting the variable that you don't want or the number you don't want in terms of the numbers that you do want. So finally, so observe this is of course now 64 minus 63, that's indeed 1. Okay, so we managed to write 1 in this way. So now what's so great about being able to write 1 in this fashion? The reason why we did all this. So finally here's what we obtained. It's 8 times the number 8 minus 3 times the number 21 So let me think of this as plus 3 times minus 21, okay, 3 times or plus minus 3 times 21. So I am writing 1 as a sum of these two numbers, 8 times 8 plus minus 3 times 21. Now here is what we will do, define n1 to be this number. So remember, we are trying to find n1 and n2, the solutions to those two congruences. The claim is you can take n1 to be just this number and n2 to be this number. Okay? So that's a claim for now. Let's try and prove this. So why is this in fact true? Proof. So let's see, what property did n1 have to satisfy? So let's just do it in this example, but you will see it's actually more generally true. n1 was supposed to be divisible by, so let's see which way was which. n1 was supposed to be divisible by 8 and n2 was divisible by this. So let me call this as n1 and this as n2. Okay, so let's see what properties, let's look at n2 first. So what properties does n2 have? n2 is just 64 in this case. It's congruent to 0 mod 8 and 1 mod 21. Okay, why is it 0 mod 8? Because it's a multiple of 8. That's more or less clear. Why is it congruent to 1 mod 21? Well, when you divide 64 by 21, you get 63 as the quotient, right? And there's a 1 left over. Okay, and that's exactly what's happening here, because there is a 63, that's the part that's divisible by 21, and then that's the 1 that's on the other side. Okay, so when you divide this number n1 by 21, because this is a multiple of 21, what's left will always be a 1. Okay, so it's kind of by design. So n2 satisfies these two congruences. Similarly, let's look at n1. n1 in this case is minus 63. Okay, so observe, it's not a positive number, it's a negative number, but nevertheless it is a solution to this set of congruences. So so this is a multiple of 21, it's 0 mod 21, because after all it's minus 63, right? It's minus 3 times 21. But here's the interesting part, it will surely be 1 mod 8. Why is that? Because minus 63, think of it as minus 64 plus 1. So this is, here's a multiple of 8, which is minus 64, and you're adding a 1 to that. So the remainder on division by 8 is in fact a plus 1. Okay? So if you take this first fellow as n2 and the second fellow as n1, they automatically satisfy the two congruences that you require of them. Okay? n2 satisfies this 0 1 congruence and n1 satisfies the 1 0 congruence. And this is a general fact, no matter which a and b you start with, provided instead of 8 and 21 you start with any two relatively prime numbers, things which don't have a common factor, perform the Euclidean algorithm on them, you finally obtain the GCD, you run the Euclidean algorithm in reverse to obtain an expression where the GCD1 is written as some multiple of the number a plus some multiple of the number b. Then you pick one of the factors as n1, the other factor as n2, they will always satisfy, they will be these 0 1 solutions, okay? These the solutions to the 1 0 and the 0 1 congruences. This is a completely general fact and a completely systematic way of finding the solutions n1 and n2. So now in this case, what are the two solutions? One of them n1 is minus 63 and the other is 64, right? So those are the two solutions in this particular example. Now these solutions from before, so these two things were things we found by trial and error. Now here's solutions which we are going to find by our systematic procedure, the Euclidean algorithm approach. So here's the Euclidean algorithm provided solutions. The Euclidean algorithm says n1 is the number minus 63 and n2 is the number 64. Okay, this is what the Euclidean algorithm gives. Now comparing with what we had before, okay, observe we had written out two solutions by trial and error, but again, so what's the difference? n2 is the same, but n1 seems different. Right? The trial and error method said that n1 is 105, but this said this is minus 63, But again, note that this is only one solution, and to get any other solution, all you need to do is, going from here to here, you can add any multiple of 168 to get a new solution. So minus 63, you add 168 to it, that's exactly going to give you plus 105. So how do you go from this Euclidean solution to the trial and error solution? Well, you just add 168, and that's of course something we know you can always do. Okay, so this sort of concludes this idea. So we have done two things really. One is we have reintroduced the 0-1 idea in this context and seen that it actually has a very nice application to this problem. Secondly, we have used the Euclidean algorithm to give a systematic solution of the 0-1 problem. Okay, often it's not the fact that the 0-1 problem gives a solution that matters. That's there in many contexts. It's being able to write easy solutions to 0-1 problems. That's been something we have used again and again. In the Lagrange interpolation method, for instance, the 0-1 problem has a very easy solution because of those special form of the Lagrange polynomials, right? Product of all the x minus x1, x minus x2, whatever, divided by something. That's something we could get by using properties of polynomials. In the example, when we talked about three-dimensional vectors and the 0-1 idea, we were able to solve the 0-1 problem more or less by using the cross product of vectors. Okay? So the cross product came in handy there and allowed us to give quick solutions of the 0-1 problem. Here, the solution of the 0-1 problem comes through the Euclidean algorithm. Okay? And you need to do whatever we said, run it in reverse to do this, and then you're done. In one step, you get the 0-1 problem. So all of this, for instance, can be programmed on a computer in a completely systematic fashion and won't require any guessing or trial and error.